What if every robot, drone, wearable, and medical device could think locally, respond instantly, and use almost no power? Neuromorphic robot brains borrow from biology to help machines perceive, adapt, and learn in the real world. We've been building toward this point, from autonomous AI minds through biology, planetary robotics, and advanced materials. Now the focus shifts to embedded intelligence, systems that can make decisions on device, use very little power, adapt in real time, and support resilient machine ecosystems at scale. Project 26 is about bringing intelligence closer to the physical world. Instead of sending every signal to a distant cloud, tiny machines gain a local, brain-inspired layer that can sense, decide, and learn where data is created. That matters because small devices face strict limits: battery, bandwidth, and response time. Neuromorphic computing helps reduce those costs by processing events efficiently, more like nervous systems do. The result is adaptive drones, wearables, implants, robots, and sensors that can keep improving after deployment without relying on a constant cloud connection. The question is no longer whether AI can be powerful. It is whether AI can be powerful when energy, bandwidth, and time are limited. Neuromorphic computing matters because it makes fast, efficient decisions possible in real-world conditions. Neuromorphic computing begins with a simple biological idea. Neurons stay mostly quiet until incoming signals cross a threshold. Then they fire a brief spike, and that event carries information to other neurons through synapses. Spiking neural networks copy this pattern. Rather than updating every value continuously, they react when events occur. That sparsity can save energy and reduce unnecessary computation. Neuromorphic chips push the idea further by placing memory closer to processing, so data does not constantly shuttle back and forth. Learning can also become more local, adapting from nearby signals and feedback. A neuromorphic robot brain works like a compact intelligence stack. Event-based sensors first notice change, not every pixel in every frame, so the data stream stays sparse. That stream is encoded into spikes, which neuromorphic chips can process with very low power. Lightweight models, including spiking neural networks and TinyML classifiers, turn those signals into perception and control decisions. Finally, a local decision and learning layer chooses the robot's action and adapts from experience. The key idea is integration. Efficiency comes from the whole pipeline being designed around events, locality, and adaptation. Event-based sensors work more like reflexes than traditional cameras. Instead of recording every full frame, they report only meaningful changes, such as shifts in brightness, motion, sound, or pressure. That creates a sparse stream of events, giving the robot less data to move, store, and process. The result is faster reaction with lower power, especially when motion matters most. Spiking neural networks treat information less like static numbers and more like events unfolding over time. A sensor detects a change, such as vibration, touch, sound, or motion. That change is encoded as spikes, where timing and frequency carry meaning. The network looks for temporal patterns across connected pathways. If a pattern matters, the system can trigger a control response, like adjusting a robotic grip or wheel motion. It can also update nearby connections locally, similar to synaptic plasticity, so adaptation happens without retraining an entire deep model. TinyML adds another piece, just enough intelligence directly inside the device. Instead of streaming every sensor reading to the cloud, a small model can recognize local patterns in motion, sound, vibration, vital signs, or obstacles. This matters when battery life is tight, memory is limited, heat must stay low, and latency cannot wait for a network round trip. Neuromorphic processing complements TinyML by handling sparse, event-driven signals efficiently. Together, they let wearables, robots, and remote monitors make fast decisions where connectivity is unreliable, unsafe, or too expensive. A neuromorphic robot is not just a sensor feeding a controller. It is a closed loop. Event-based sensors report changes, like motion, edges, or sudden light shifts, instead of streaming every pixel. The neuromorphic processor turns those events into fast, low-power signals. Pattern recognition gives the signals meaning, such as obstacle, target, or grasp point. Local decision logic then drives the actuators immediately. After the robot moves, the environment changes, new events arrive, and the loop repeats. That feedback is what lets behavior adapt in real time. Picture a search and rescue micro-drone entering a damaged building. Its event camera reacts only to changes: smoke movement, heat flicker, shifting debris, or human motion. A neuromorphic chip processes those spikes locally, so the drone does not need a cloud connection to act. It can avoid obstacles, conserve battery, and keep searching when networks fail. The same pattern applies to farms, factories, and field robots: fast sensing, low power, and adaptive decisions at the edge. Healthcare shows why local intelligence can be so valuable. A wearable can notice changes in gait, fatigue, stress, or tremor without streaming raw biosignals to the cloud. An implant can respond immediately to a patient's own patterns instead of waiting for remote analysis. Prosthetics and assistive robots can adapt as the user moves. The result is care that feels more continuous and personalized, while keeping sensitive biological data closer to the body. The same approach can support infrastructure and environmental monitoring. A bridge could notice unusual vibration before damage becomes dangerous. A forest sensor could detect early signs of fire without constantly streaming data. Neuromorphic sensing makes this practical because intelligence sits where the signal is. Tiny devices can filter noise, decide what matters, and send only meaningful alerts. That saves power, reduces network load, and allows infrastructure and ecosystems to be monitored continuously, even in remote places for years. Now imagine intelligence becoming as ordinary as electricity, not trapped in one supercomputer, but embedded in roads, hospitals, farms, robots, and habitats. By 2050, neuromorphic machines could help form a planetary nervous system, sensing locally, learning continuously, and responding before problems become crises. Project 26 gave us the intelligence layer: event sensors, spiking networks, neuromorphic chips, TinyML, and local decisions working together. The key shift is clear. AI moves from distant clouds into low-power devices that sense, adapt, and learn in real time. Next, we scale from smart machines to a sensory planet, then towards autonomous agents, decentralized science, and resilient systems.